Force of gravity. These slides are, oh, actually, I don't think I've put these slides up. I will put these slides up today. Easier.
Is this stuff going to be on the quiz?
No, this is new stuff. This is forces. So we've done dynamics, Newton's laws. And now we're going to do forces. So this one is checked, and this one is not checked yet. We're just starting this. Quiz will be on this stuff. If you look at the back there, we're kind of skipping ahead a little bit, but I feel like it's good for you grade 11s to know this. There's an FG here, and that FG says mg. Yes? And what number is g? Yeah, it was a masked 9.8. Back here, sorry, back on the back there, there's another FG. And it says big G times M1 times M2 over R squared. That's this formula here. I'm just going to write it big for you so that you can see it. This you can use to figure out any force of gravity, not just with the Earth, any two objects. Okay. This is the force. This G is a constant. Gravitational constant. I think it's 6.67 times 10 to the negative 11. Can somebody confirm that for me? Just Google gravitational constant. Thank you, Declan. What do you think this M is for?
Yeah, 6.6. Mass. First mass.
Thank you, Declan. This is the mass of the first object. Thank you, Sam. We'll say mass 1. And what's little m? Yeah, we'll just say mass 2. You can say M1 or M2, or you could say mass of planet and mass of satellite, or you could any two masses, it doesn't matter. I just like doing big M and small m. And then R is the distance between the objects. That's the formula. You'll never have to memorize that formula. I'll give you the formula. But you have to know how to use it. And you don't have to memorize the constant. I'll give you the constant. Some of you are wondering, why did you use R? Radius? For the distance instead of D.
Because it's range.
Close.
Radius.
Better. So, in the day, Newton, Isaac Newton, who was the discoverer of this, so history says, he was looking, you know how I went off on that rant this morning about you guys learning and everything?
Yeah.
And it takes us like a long time today to get to the edge of human knowledge, right? And back in the day, all you had to do was walk outside. You just walk outside and look in the sky. Nobody knew what was going on up there, right? Stars and planets and everything, nobody knew anything. But they knew that those lights were moving across the sky. And you could calculate mathematically and predict where the lights would show up and where they would go. And Newton was figuring out, he was one of the first people, he and Kepler and a couple other people were figuring out that these were planets orbiting a star. And he wanted to figure out how to calculate the force between those objects. And so he used this formula, and R was the radius of the orbit of the planet going around the sun, which is the same as the distance between their centers.
No,
Does that make sense?
doesn't make sense.
Okay.
Wait,
That-
is there the distance stays the same throughout the entire orbit?
Yeah, it actually does change a bit, but in general.
Something like that.
Yeah, it's an elliptical orbit, but you can still use this as if you use the average distance.
I see.
That's why, by the way, that's why ice ages happen. Because our orbit does change a bit, and it's an ellipse, and it does kind of have these patterns over tens of thousands of years. And so if we get farther from the sun, that's when you end up with an ice age. And
What about global warming?
yeah, global warming is happening way, way, way faster than,
It should.
It should
than,
be.
well, yeah, like,
uh,
so ice ages come and go over millions of years. Climate change is happening in like 20 years. So it's too fast. It's too fast. Okay. So gravity can attract any two objects. You put in their masses and their distance apart, and you get the force between them, and you have to multiply by the universal gravitational constant, which is the same for all objects. Doesn't matter what it is. Put in the mass of the first object, mass of the second object, and the distance between their centers. A very interesting point is this little number 2 right here, this squared. This, you guys have learned a little bit about relationships, yes?
Yes.
With Hooke's law, what type of relationship was it? Linear. What type of relationship do you think this is?
Quadratic.
It's close. Quadratic sounds very good. A squared relationship is quadratic.
Inverse.
Ah,
Nice, Sam.
very good, son. This is, now, the relationship between force of gravity and mass is directly proportional. It's a linear thing, right? If you double the mass, you get twice the gravity. Yes? But with distance, it's an inverse square relationship. What that means is that if I triple the distance, I get 1/9 the force of gravity. Why if I triple, why do I get 1/9? It's squared, and it's inverse. So if I go 5 times farther away,
1/25.
very good, I have 1/25 of the gravity. So gravity drops off really quick as you get farther away. That's why for Pluto, the orbital time is so long, because there's so little gravity out there. It's just really, it doesn't need to move very fast, and it can keep falling around the Earth. Okay. Try it. says, what is the force of gravity exerted on a 70 kilogram astronaut who is standing on the Earth?
The thing is behind you. Well, it's just half of whatever
Is center RE or ER?
ER. Oh no, R. R. No, ER. It's ER. No, it's ER. Center. No, because that'd be center. That'd be like French.
That's like can. No.
I'm not sure.
It's center for 100%. Centre. In French, it's centre.
Why did I give you the radius of the Earth?
Because it's the center of the object, it's the center.
Good. In our formula, did I go through this? So you start with your
Oh, you can.
the distance between, you think you're touching the Earth, right? And we are. We're on the surface, but we're a long way from the center of the Earth. And so we have to use this as our distance from Earth, because we're that far from the center. The Earth's pretty big, 5.98 times 10 to the 24. Now I'm going to do something a little bit interesting here. Have I taught you guys how to use the capital E's on the calculator?
No.
Okay. I'm pretty sure I have, but that's okay.
You have to know. You really have it.
If you want to put the gravitational constant in your calculator, what was that number again?
6.6.
Very good. 6.67 times 10 to the negative 11. If you want to put that number in your calculator, you can put in 6.67. And then, maybe I'll do this over here so you guys can see. Like that, maybe. You plug in your 6.67. And then what you're going to be tempted to do is you're going to be tempted to say times blah, 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 blah. That's going to make for mistakes. So what you do instead is you find on your calculator, on a graphing calculator, it's this button right here. Whoa. See this capital E, capital E? That means times 10 to the power of. So you hit second function and then you chunk this key. So I'll zoom out. So you hit your second function and you'll see the arrow go up on your screen, right there. And then you hit the capital E, capital E. And you'll see a little capital E show up there. And this is the same as 6.7 times 10. And then you just hit negative 11. So you hit your negative button and you hit 11. And that is the same as this. Now, put your hand up if you do not have a graphing calculator. Okay. If you do not have a graphing calculator, that's okay. You're going to look for a button that says maybe EXP. The button might say that, and you'll click it and it'll say a little times 10 to the power of. It might be just a capital E. It might be a capital E, capital E. It might say times 10 to the power of X. It might say that. Any of those things, and these might not be buttons. It might be a little symbol above the button, so you have to do the shift or a second function or whatever. Try to figure that out on your calculator right now, because all of these problems have big numbers like this, big scientific notation numbers. Okay. Let's multiply this by the mass of the Earth. If you go times, and this is 5.97 times 10 to the power of 24, that's the mass of the Earth. And then we're going to, before I put in the mass of the astronaut, I'm going to do something weird, just to show you. If we divide that by the radius of the Earth, so I'm going to divide by, what is it, 6380 or something?
6.38 times 10 to the 6.
What's in the six? Oh, meters.
Wait.
Yeah, no, that's right. 6.38 times 10 to the 6. And notice that this, so this is 6.38 times 10 to the 6. That's 6 million meters, which is the same as 6,000 kilometers. Okay, but we want to put it into meters. Ashley's right, we want to put this into meters because we're using our physics units, kilograms, meters, seconds, and all that stuff. So if you get 6,380 kilometers, we have to multiply that by 1,000 to get the meters. Okay. So if I put in this gravitational constant and the mass of the Earth and divide it by the radius of the Earth squared, so I have to punch squared there. Notice that because I have the capital E when I square it, it's squaring this whole number. If you type in times 10 to the power and you do your x, y times 6, and then you square it, it's not going to do the whole thing. So you're going to make mistakes. Okay? That's why we do this way. What do you think is going to be the answer when I hit go? I haven't put in the astronaut's mass yet.
9.8.
Oh.
9.
Ashley says 9.8. Why would this be 9.8?
Gravity.
Lauren, tell you. It's the force of gravity on Earth, because we're just multiplying that by the mass to get gravity, right? So let's find out.
Is that 9.8? Yeah, 9.8.
It's pretty close. If we, this mass here is a little bit, it could be 5.97 or 5.98. You read it different places. There's a bit of rounding and stuff. This is why we just take mass and times by 9.8. Because the force of gravity on any mass on the surface of the Earth will be this. Okay. So let's just do this quickly. Whether you do just mass times g, which really this is little g for Earth, right? Or you times by all the numbers. You should get somewhere around 700, 680 or something like that.
Yeah.
How much is it?
686.
686?
Yeah.
Somewhere around 686 newtons. Put your hand up if you got something like that. Good. If you didn't, go back and watch the video and recalculate this out. If it's close, if it's 690 or if it's 684, don't worry, that's fine. Okay. Could you use this to figure out the acceleration of gravity on a different planet?
Yeah.
Yes.
Yes. What would you need to know?
The radius of the planet.
You need the radius, and
The mass.
you need the mass of the planet. But if you have those two things, you should be able to find that planet's 9.8. It'll be different, but okay. Try this.
Okay, we don't so we like this. The altitude plus this. And you can use the control because it's center, so if you
So now we take our astronaut, we put her up in space here. She's way up there. The word altitude is very important. What does altitude mean?
From sea level.
Good, from sea level. So, can we just use this number for our
No.
distance?
No.
We cannot, right?
You need the radius of Earth as well.
Yeah, so this is the radius of Earth, is 6.38 times 10 to the 6 meters. And we also need to add in, or we need to add that to our altitude, which I said was 3.19 times 10 to the 6 meters.
Oh, so it's just like half the radius. Oh, it's exactly half. Is it? It's not with exponents and stuff.
You're right, Sam. You're right. You gotta add them together.
9. But Mr. E,
Yeah.
where did the universal gravity come from? Like how do people know it's a fixed point?
The reason that we know it is because a bunch of people did a bunch of experiments, just like you did with Hooke's law. And they graphed out all the forces and the masses and the radii and everything. And we found again and again and again that we get a constant value for this.
I see.
And that was the value. Where it came from, you have to ask God that. We don't know where it came
That's
from.
true. Are you
Well,
in-
actually, there's a little bit more to it than that.
Are you in the theory that we're in an expanding universe, contracting universe, or equal universe?
Oh, that's a big question. Evidence would tell us that the universe is expanding. And actually, when I was your age, there were multiple theories, but the idea was that it's expanding, but it's probably getting slower as time goes on because there's all this gravity force. And so as it's expanding, everything's kind of pulling it back like a spring stretching. And so one of the theories when I was your age was that the universe would get to a certain point and then it would collapse back in on itself. And then some people said that the whole thing really should be in an oscillation because you get these repulsive forces and then it'll spring back out again and then it'll collapse again. But since I've been teaching, it has been found that the universe is expanding and it's not slowing down. It's actually speeding up.
It's exponential?
it is getting faster.
So you like the cone theory?
So most physicists now would tell you that eventually the universe will be so spread apart that if you're in our galaxy, you will never be able to see anything else.
I heard that 94% of the universe is undiscoverable from now on. Because it goes
That's the theory.
dark,
That's the theory.
dark stuff.
Because space is expanding faster than the speed of light. And so the distance between objects of matter are getting farther away than we have time to see. If that makes sense. The light never makes it back to us.
So the lights.
But there's a big but to that. There's an assumption there, and any physicist will tell you this. The assumption is that the laws of physics, and particularly the speed of light, is the same everywhere. Not only in space, but in time. And that's a big assumption. It's a big assumption. Do you know what we're like? Imagine a housefly in your bedroom on a sunny morning, okay? And it's only got 24 hours. And it cannot get outside of the house. But it can see out the window. And this is a very intelligent fly. Could the fly work out when and how Rome fell?
Oh, didn't Caesar get stabbed by his homies?
Yes.
That's about what we're trying to do.
Yes, because the
Wait,
kid.
We've been watching relatively for way less than 24 hours. Like, we've only been writing stuff down for a couple hundred years.
I'm gonna say yes.
So we've been watching for an extremely short amount of time. Like, just a crumb in the age of the universe. And we can't get anywhere. We literally, our furthest spacecraft just left our solar system. That's nothing. It's nothing in the universe. There are billions and billions of stars in our galaxy. Each one of them has a system like ours. And there's billions and billions and billions of galaxies. So we really haven't been anywhere, and we haven't been watching for any amount of time. And we're trying to work out how this whole big juggernaut of stuff is working. And so my hunch is that we're probably missing something.
Really?
Well,
That's my thought.
One of the crazy stories that I heard is that, like, I don't know what machine it was, but it was something to prove that gravity, I think it was something to prove that gravity was a wave.
Pause that thought. I do want to continue this. I've got Arsam and I've got Kai. I do want to continue this conversation, but I'm videoing and I feel like I should get through this bit. So if we go here, what am I going to put for R?
Oh, you're gonna add those two?
I'm going to add these two together. Now, this is 10 to the 6, and this is 10 to the 6. So I can just add these two numbers together. Okay. I can say 6 plus 3 is 9, and 9.4, 9.57, right?
Yes.
Is that right?
Yes.
But I've got to square that whole thing. And so if I calculate that out, what number do I get?
305 newtons, like for the whole thing.
305?
Newtons for
That sounds about right. 1.5 squared is 3/2 squared is 9/4, so 1 point. Yeah, it's a little bit less than this. So originally it was 686, right? So a little bit less than half makes sense because the altitude, I don't know if you noticed this, but this altitude is half of this radius. And so we took our distance originally and we increased it by 1.5. 1.5 squared, 1.5 is 3 over 2, and you square that, you get 9 over 4, and if you flip that over, it's 4 over 9, a little bit less than 1/2, and so this is a little bit less than 1/2.
Wait, what about,
half of what we had before.
does it have to be 10 to the 12?
No, no, if you're adding these together,
Oh, those.
you don't have to multiply those, no.
Oh,
If you multiplied them, you would.
I see.
Yeah. This is 6.3 million plus 3.2 million,
Oh,
right?
yeah.
Makes 9 point whatever million.
Oh, okay.
You don't have to fully understand what I just said, but you do have to understand how to do these calculations, and I would get very comfortable with your calculator. If you don't have a calculator, you really need to get one. Get comfortable with your own. Okay. Try this. Have you ever looked beside yourself and thought, am I attracted to this person? You're about to find out just how attracted you are to your lab partner. So no more Earth. No more Earth here. So there's no Earth's mass. And I just guessed two random people. This is not particular people, but. So if one person has a mass of 55, we put in our same regular formula. And we're going to put in 55 kilos and 65 kilos and 50 centimeters apart. What would I change that to?
Meters.
Good. So how many meters is that? 0.5. Good. So we have to put in our big clunky constant, but now we just get 55 and 65. We put that all over 0.5 squared. And you're gonna get, that's 0.25, so it's, I said 300, 300 a quarter is like 1,200, so.
This is how much I'm attracted to.
Something about right.
It's gonna be like 6 times 10 to the negative 9 or something like that.
9.5 times 10 times
9.5?
Yeah, 9.
I was way up. 9.5 times 10 to the
Negative 7.
negative 7.
Is that right? Maybe I did it wrong. Hold on.
Oh, yes.
Oh, no.
No, that's right. It's about, this is 0.25, right?
Yeah.
So you got times this. This is about 300, 400. Times 4, 1600. I don't know. Can I have confirmation? Yeah? Very good. Yeah, okay. Okay, good. And this is what? So, times 10 to the negative 7. Okay, so 0.000000095 newtons. So the answer is yes, you are attracted to the person beside you, but not very much. Very, very little. You're more attracted to, you're actually more attracted to the concrete pillar in the back than you are to your lab partner, I'm sorry to say. I think that's the end of this. Okay, so that's universal gravity. And there's another set of slides to come, but I'll stop this video here. How long did that go?